Welcome. Good morning. Last day we started talking about the sampling distribution of a proportion, so one sample proportion. And what we also said was that, okay, we're going to develop these distributions for a lot of different statistics. So not just one sample proportion, we're going to look at how do we compare two sample proportions? How do we look at multiple proportions, more than two? And then we're going to move into means. How do I look at a single mean, multiple means? And so we're going to develop the framework here for just one sample mean, but then we're going to apply that same framework to all these different scenarios. Okay, and so last day we said, so just as a little bit of review, we said that the sampling distribution of p hat, which is one sample proportion, okay. That doesn't look like one, does it? A little bit better, maybe. So the sampling distribution of p hat, which is one sample proportion, which is going to be the type of question that we're looking at right now. Okay, so here, this is the type of question we are working on. I like to break it up so that we're talking about different question types, because then your first job is to read a question and figure out what type of question it is. And then you'll be able to go from there and decide what to do. And you'll have a clear path. Once you've decided what type of question you have, then you have a clear path that you need to work through. Okay, so I would argue that deciding what type of question you have is the hardest part, and then it'll all kind of run smoothly. Okay, so the sampling distribution of p hat, which is one sample proportion, can and maybe I'll just end it here. I don't want to continue it as a sentence. It got weird because I wrote this kind of big note here, but maybe I'll do this, is that p hat follows a normal distribution. Okay. So then with a normal distribution, we're back in familiar territory, right? A normal distribution, because we know the shape of the normal distribution, we know some of these attributes already that we have established. You know, we know how to use z-scores to find probabilities, which are areas under the curve, right? So just knowing that it follows a normal distribution, we're kind of on easy street now. We just need to know, okay, well, that's weird. A proportion follows a normal distribution. Okay, we've seen that before with the binomial, right? With the normal approximation to the binomial. And there is a link there, but it's not a link that I expect you to see. But if you kind of work at it long enough, you will start to see the link that, okay, a binomial, it is basically just what we're looking at here for a one sample proportion question. Okay, so it follows a normal distribution with a mean of p, which is the population proportion. One problem that we established last day was, okay, well, unless I have some idea of what p might be, the population proportion, then my best guess at what p is p hat, right? And so that's what we would use as an estimate. But in theory, this is what it would look like. And then it would have a spread or a standard deviation of p times 1 minus p over n. Now, a couple of things that I want to point out here. Usually, instead of writing 1 minus p, I usually clean that up by writing q instead. Okay, so Q equals 1 minus P. I just find that it looks a little bit cleaner to just write P and Q instead of P and 1 minus P, but I mean, Q is 1 minus P, so it doesn't matter as long as you're aware of what's going on, okay? And this chunk here is the standard error. Now, this is where things get a little bit weird, okay? Because, well, we know that this space in the normal, in the notation that we're using here is really for the standard deviation. But the standard deviation is specific to the distribution for one observation, right? And so for single observations. And so we can't use the word standard deviation. So we use the word standard error instead. So the standard error of P hat, which is basically the standard deviation, but standard deviation is specific to one observation, so we can't use it. So we had to develop some slightly different terminology, but they behave the same way, right? It tells us the spread of the distribution, and so then we can just use that, right? One thing that we notice here is that, and maybe I shouldn't use pink so soon, right? But here, unless we have, and there's a reason that I'm being very picky about saying, okay, unless this is true, so unless we have some hypothesized value of P, because if we know P, there's no sense in trying to use P hat to try to figure out what it is, right? Because that's like saying, oh, I know that the average price of milk is this, but I'm going to take a sample to try to figure out what it is. That makes no sense, right? So same thing, right? I know that the average, or sorry, I should use proportion examples. I know that the proportion of females born in a hospital is this, but I'm going to take a sample to try to figure out what it is. Again, makes no sense, right? So our goal is to avoid having to collect the entire population, right, and figure out the population proportion. Our goal is instead to try to use what P hat gives us, the sample proportion. So we just want to use a sample proportion to try to figure out what the population proportion might be. And that is inference, right? Taking sample information and trying to figure out what that is in terms of the population. So here, unless we have a hypothesized value for P, a hypothesized value for P, which is the population proportion, we'll never know what P is because, like I said, that makes no sense. The population proportion. So unless we have a hypothesized value for P, we will use P hat, which is the point estimate for P. The point estimate for P, and also our best guess, right? That's what the point estimate is. It's our best guess at what it might be. Okay, so our best guess, we will use P hat to estimate the distribution. Okay. So then what we're saying is that P hat follows a normal distribution that's going to be centered on P hat. There's no reason to think that it wouldn't be centered there. It's our best guess, right? But it's going to have some spread of P hat, Q hat over N, right? So notice how I'm cleaning this up a little bit, and Q hat is just 1 minus P hat. we've seen that notation before in the binomial, so I'm not afraid to use that notation. Okay. So what does this mean? Well, some cool things are that this is the center of the distribution, p hat, right? So that's where we assume things are centered. But then we understand that if I were to take a completely random sample, so even if this sample proportion that I have is, perfectly representative of the population, I understand that if I were to go out and collect a completely different sample, even if it's randomly selected and it's all a good sample, then that sample proportion would be slightly different, right? And so we have that understanding that there's going to be variability in our sample proportions, and it turns out that that variability can be captured by the square root of p hat q hat over n, or approximated at least. Okay? And so just as a little note, right? What's fun about these questions is that p hat is the sample proportion, and it's the number of successes divided by n. Yeah? So in order to solve these problems, notice how, okay, p hat shows up as the center, so it's the mean, and it shows up here in the square root, and then q hat is just 1 minus p hat. So far we've only really used information on p hat and then n, but n is incorporated in p hat. So what's cool about these questions is we only really need 2 pieces of these three to be able to solve the problems, right? So we only need to know 2 of these 3 pieces of information to solve these problems. We'll bump it over, line it up, right? So we need to know if we have p hat and n, right? Then p hat and n, I can find the number of successes by just multiplying the 2, right? And so here I can rearrange this thing. Maybe I'll just do p hat n is the number of successes. Oops. And the number of successes divided by p hat, that'll never happen. So this is the only other setup that we use, right? So sometimes a question will give you, okay, 40% of people in a sample of 1,200, for example. So then you have p hat and you have n, and then you might have to find the number of successes, right? Or usually I'll give you, 375 people out of 800 people that were surveyed said this, right? That's the number of successes over n, right? So your 2 different options. So questions might be worded as, let's see here, 40% of people in a random sample of 1,200, right? So here, this is your p hat. P hat is 0.40. Remember, proportions are not percentages, right? But often we report proportions as percentages by multiplying by 100, right? So, but proportions in our calculations have to be decimals. So our p hat is 0.4 and our n is 1200, right? Or we might say 375 out of 800 randomly sampled people said blah, 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 blah. Right, so now you have the number of successes is 375 and your n is 800 in this case. And just as a side note here, the number of successes, I know tons of side notes all over the place. The number of successes can be denoted by X. Okay. So sometimes you can denote the number of successes. So instead of writing out the number of successes, you can just say X. X is 375. So for example, here I might say X is 375 instead. Yeah. Okay, so I'll call that the end of our review. We didn't really end up talking, we didn't have time to talk about these two different wordings that we can have, but it's a nice break because it's a page break. So I'll call that the end of our review. Okay, so if we know that these sample proportions come from a normal distribution, let's remind ourselves of the conditions, right? There were conditions to using this normal distribution. Yeah. So we can use the fact that p hat follows a normal distribution centered on p with the root of p times 1 minus p over n if the following conditions are met. Yeah. There were two main conditions, and then I brought up an optional condition, but you don't have to check that optional condition. The only reason I'm mentioning it is if you're going through some of those old practice problems that I've posted at the bottom of our Moodle page, then those would use the optional condition. And so I just don't want you to be thrown off by it. And really, once you get the hang of it, there's no harm in checking that optional condition. But the first condition is the independence condition. Okay. So the main independence condition is, okay, we have to be able to assume that our sample, everyone in our sample is independent of each other, right? Or all the observations are independent of each other. Now, the usual way that we check that or ensure that is by randomly selecting our sample, right? So first, I'll call it random. The sample was randomly selected, or we assume that it was, that doesn't look like a bracket, or we assume it was randomly selected. That's going to happen a lot, where the question doesn't actually say that this was randomly selected, but then because these are conditions that we're relying on, then what's going to happen is we're going to have to say, okay, well, I don't know that it was randomly selected, but I assume that it was randomly selected, and so I can apply these methods. The second condition for independence is that optional condition, because it's very rare that it's an issue, right? So I think if you ask the general population, about, how big of a sample size should you be getting, I think everyone would agree that the bigger the sample, the better, right? But in the independence situation, right, if we are trying to assume that all the observations are independent of each other, that becomes a problem when we've collected too much of the population, right? Because then you're opening yourself up to sampling from the same household, or just having dependent observations in your sample. So to try to avoid that, you try to collect less than 10% of the population. Yeah, today you're in the right class. And so we collect less than 10% of the population to try to preserve independent observations. So the sample size, and maybe what I'll say is I'll call it the 10% condition. The sample size is less than 10% of the population in order to preserve independence. In order to preserve independence. Okay. So that one's optional, but it's important. So there's kind of two categories. So there's the independence condition, which is basically just making sure that we have a random sample. And then there's the normality condition, which we've seen before. Well, we saw it last day too. But the normality condition, we have to check the success failure condition. Which means that we have to have n times p greater than or equal to 10, and n times q greater than or equal to 10. But because we don't have, unless we have a hypothesized p, so there will come a time next day when we're going to have a hypothesized population proportion. So then you would use that. And that can get confusing, right? If you're doing a hypothesis test, then the conditions that you check are slightly different, but we'll outline that. Okay, and so unless we have a hypothesized p, we use p hat instead. So then we're going to check n times p hat has to be greater than or equal to 10, which is the number of successes, you'll remember. And n times q hat has to be greater than or equal to 10, which is the number of failures. Okay. So, let's see here. Okay. One thing is that if we're trying to detect a really small p or q, or if we're dealing with a really rare event, then we're going to need to increase our sample size quite a bit in order to meet this criteria, right? So it's just making sure that we have a large enough sample size to be able to detect what we're trying to detect, right? So in rare cases, or in the case of rare successes or failures, right? It doesn't matter if p hat increases. So if p hat is really high, then Q hat is of course the opposite of it. So it would be really low. And if the probability of success is really low, then the probability of failure is really high, right? So it doesn't really matter. So in the case of rare successes or failures, we would need to increase our N in order to satisfy this criteria. Satisfy the success failure condition, I'll say. Which makes sense, right? You wouldn't collect a sample of 20 people if you were trying to detect some rare disease, right? Intuitively, we understand that that's not going to work, right? You're not going to be able to find anything, right? So then you would collect a larger sample in order to hopefully capture some of those rare instances. So these are the conditions that we check, right, in order to build what we call a confidence interval. Okay? So the above conditions / assumptions, I use those two words interchangeably, right? So these things that we've outlined have to be checked before we can do a confidence interval. The above conditions / assumptions must be checked before we can build a confidence interval, which is what we're talking about today. So section 5.2 is confidence intervals. And usually I just abbreviate them CI for one sample proportions. For one sample proportions. P hat. Okay. So where we kind of left off last day is, all right, so if we have checked these assumptions, then we can draw this normal distribution, right? We can draw this beautiful normal distribution. And what we've said is that, okay, if we've checked those assumptions, then we can assume that that distribution is centered on our point estimate, and the standard error of P hat is approximated by P hat Q hat over N. Okay. Now, if we kind of put our blinders on, right? And I asked you to find how many standard errors would I need to go around P hat to capture the central 95%, right? I would have to move out 1, 2, right, from the 68, 95, 99.7 rule. And so what we're going to do, the confidence interval, is we often use it instead of just reporting one sample proportion, right? Because we also understand that, well, this is from one sample. And so if I considered another sample, it would be slightly different. So instead, what we do is we build this interval of plausible values for P hat. So instead of, instead of only reporting the point estimate P hat, and then I'll put in brackets, right, which would change if we collected a different random sample, which would change if we collected a different random sample. So instead of only reporting the point estimate p hat, we typically report an interval of plausible values. We typically report an interval of plausible values. So remember, our goal for inference is to take that sample information to learn about what the population proportion might be. Now, because of how sampling works, and sometimes, you know, we are representative of the population, and then there are rare instances where we are not. Right? So we don't actually know if we're capturing that population proportion. And so that's why we're only going to be 95% confident or 99% confident. But the goal of a confidence interval, that's probably the last time I write it out. Here, I'll define that shortcut or shorthand. So the goal of a confidence interval is to develop an interval of values. So an interval of values that might capture the population proportion. That might capture the population proportion. And I say might because we're only going to build 95% confidence intervals, 99% confidence intervals. And so we're not going to be 100% confident that we capture this interval, right? And there's reasons for that I'll show you. Okay, and so our goal is to kind of cast this net of an interval, and we're going to be some percentage confident that it captures the population proportion. Okay, and so how do we build this thing? All right, so if we want to build, let's start by building a 95% confidence interval. So a 95% confidence interval, well, okay, so if I have this normal distribution and I know it's centered on p hat, then I also know that I've got the empirical rule that I can rely on. And so I can say, okay, well, here is 68%, right, around p hat. And then I can move to 95%, right, to there. Try to highlight. Okay. Which means that I have to go the equivalent of 2 standard deviations out. But remember, for p hat, the standard deviations are now called standard errors, and we have that formula for finding the standard errors. And so here, this is really going, oops, plus 2 standard errors of p hat, and this is really going minus 2 standard errors of p hat. Yeah. So now we're going to have this interval of values of proportions, And we usually use, so the default is going to be a 95% confidence interval, but we'll get there where we develop different types of confidence intervals, different confidence levels, they're called. Okay. So 2 standard errors of p hat. Well, what does that look like? Well, so here, if I start in the center, then I'm going to go an equal distance around. So I'm going to go plus minus. So then I get p hat plus minus, oops, I skipped the 2 times the standard error of p hat. Now this 2 is an approximation. So I'm just introducing it with something that we know, okay? But here, this 2 is called the critical value. And that's what determines the confidence level. Determines the confidence level. Yeah. If we wanted to be particular, right, and we do, then what we're going to use instead of 2 is we're going to use 1.96. Okay, so this is an approximation. 2 is an approximation. Right, for a 95% confidence interval. And so what I want to do is I want to look at, okay, so if I have just a normal distribution, so a Z distribution, right? Because Z scores are the number of standard deviations I am from the mean, and the standard deviations in this case has morphed into the standard error. And so here, if I'm centered on 0, then if I want to capture the central 95%, okay, then I'm going to find that the easiest way to do it is to have 5% left over in the tails. And so I have 2.5% and 2.5%. So I can find the Z, right, is going to be from my table. I go here and I'm trying to find the closest area in the tail, because remember, so it's been a while since we used our Z table, right? And we don't actually need it. I'm going to show you a shortcut, but I also want to show you where it came from so that you can feel confident developing any confidence level. So here, the table entry gives us the area to the left. So I'm going to search this table for the area closest to 0.025, right? 2.5% divided by 100, 0.025. And so what do I get here? 0.025. Here it is. Bangarang. Okay. So I can map this back to negative 1.96. Now, negative 1.96 is really close to negative 2, right? I don't think there's any argument there, but you just kind of have to wrap your head around it. And so here, this actually turns into negative 1.96, or Z equals negative 1.96. And then by symmetry on the upper end, right, this is also 1.96, but the positive version, right, because we're going above. So Z equals 1.96. We notice that Z equal to plus minus 1.96 is really close to the approximation of 2, right? So instead of using 2, we're going to be a little bit more proper and we're going to use 1.96, okay? And you don't have to go through and find this, although I don't think it's that difficult. You have the skills, you can do it, but you're not going to have to go through and use the Z table every time, okay? And so what we're going to do is we're going to denote these critical values. Now, where did I write that out? Oh, here. So the critical value is going to be denoted by Z star. Okay. The critical value for any confidence interval, and yeah, we're going to stick to the ones that are in the table, but the critical value for any confidence interval will be denoted by Z star. Okay. And maybe I should use, instead of confidence interval there, or CI, I'll say confidence level will be denoted by Z star. Sorry. Yeah. So instead of using the Z table and finding it every time, right, we have a shortcut that I want to show you. And so to find Z star, we can use a shortcut. Which is in table C, or the T table. Okay. And so in that, this document that I posted on Moodle, we start off and we have the Z tables, that's great. And then the negative side, and then the positive side. And then we have this second table, which in this case is called table C, but it's the T table. Now, we are going to use this table, of course, but for now, we're just going to focus on looking at these confidence levels. Hey, this looks promising, right? And then we're going to ignore everything in between until we hit this Z star line. And so what I'm going to do is I'm going to copy this into our, and maybe I don't even need the top part for now, into our notes. And let's see here, I think. And the whole thing. Okay. So here, these keep going, of course, But what I want to do is I want to copy that so it's all staying together. There. Magic. Okay. So we've got these confidence levels up here, and I'm only going to make you use these confidence levels. So I would never ask for, although I have accidentally asked for a 97% confidence interval in the past, and you have the tools, right? I just showed you how to find the Z star for that, right? If you wanted 97% here, you'd have 3% split between the tails, so 1.5 instead of 2.5. And so it's very similar, right? So you can solve it, but it's not something I'm expecting you to do. Okay. And so we've got these confidence levels, And then, like I said, we're going to skip down, just scroll through everything. In fact, I'm going to kind of blur that out and just focus on the Z star line. Okay. So here, if we go to 95%, right, it tells us that Z star is 1.96. So that's really nice, right? That we can just go ahead and use this 1.96 without doing the math or kind of the work that we did earlier, right? Drawing out the curve, putting 95% in the middle, figuring out what the tails are. Right here, it's just given to us. So now if I asked you to do a 99% confidence interval, well, we don't know how to build the interval yet, although you do, right? We just haven't done it. Well, if I'm asking for a 99% confidence interval, what would my critical value be? My critical value would be 2.576. Okay, so I would move 2.576 standard errors away from the point estimate. Okay, so in general, a confidence interval has the following form. It's going to be a point estimate plus minus, because we're going to use that point estimate as our best guess, and then we're going to build an interval around it, right? So we're going to go down a little, up a little, and we have to go in equal distance, of course. And it's going to be a point estimate times the critical value times the standard error. And I'm going to have to bump this over here. Standard error of the point estimate. So each point estimate is going to have some standard error, right? So basically it's standard deviation. So in our case, right, for one sample proportion, our point estimate is p hat. And the critical value that we use is what we call Z star. And the standard error of the point estimate, we can just denote it by this for now, right? But we also remember what it is, right? It's the square root of p hat q hat over n. Okay. But I want to just leave it like this for a little bit longer while I point out that this plus minus chunk, right? Everything that you're adding and subtracting from your point estimate is called your margin of error. Which I usually just abbreviate ME, but MOE is an option as well. Okay. So the margin of error comes up, especially in, research papers and stuff like that. And so if you're reading research papers, then it's good to be aware of what the margin of error is. But the margin of error is just the plus minus chunk of the interval. Okay. So now what we can develop is, well, we can replace just this generic standard error of p hat with the actual formula. And so we can have p hat plus minus Z star times the square root of p hat q hat over n. Okay. Clean this up a bit. There. Okay. Good. So before we do an example, there's a formula for, and I shouldn't say a formula, there's a prescribed interpretation of any confidence interval. Okay, so when we interpret a confidence interval, we're going to have to emphasize that we're trying to capture the population proportion in this case, right? Or whatever parameter we're talking about, right? And so to interpret any confidence interval, we use the following format. Okay. And there's a couple of different variations, but I encourage you to stick with the one that I'm giving you. Okay, so it will become very tedious, but as long as you stick with this one, then or kind of some version of it, then you're going to be safe, because there's many ways that you could misinterpret the confidence interval, such as it's not a probability of capturing the population proportion, right? It's some confidence level that we have captured the population proportion. So those are minor differences that are significant. So to interpret any confidence interval, we use the following format. So we would say I usually just start with we are some percentage. So we are blank percent confident. And here's where you would put maybe 95% or something like that, depending on what interval you built. We're blank percent confident that the interval from here to here. Now, you always want to start with your lower bound, right? If you're going back to that normal distribution that we drew up, you always want to read from the lower bound up to the higher bound. Otherwise, there is no interval from the higher to the lower, right? So the lower to the upper bound. So we're 95%, or we're some percentage confident that the interval from the lower to the upper bound captures the population and blank. Okay. Where blank is the parameter, such as proportion, right? Okay. And usually that the parameter, the population of interest, right? It's part of the question. Okay, and so I've got an example lined up here, but let's just focus on the lower and the upper bound before we can do the rest here. Okay, so when we calculate the confidence interval, p hat plus minus z star times the root of p hat q hat over n, we calculate that and we find that this interval is between some lower bound and some upper bound. Okay. So this is how we should report our confidence interval. So this is how we write the interval, right? Order matters here, right? Because there is no interval from the upper to the lower. Order matters because there is no interval from the upper to the lower. Usually that's what I have questions about when you guys are working on your assignments later, is because we have the plus and the minus, most people want to deal with the plus side first and then the minus side, but the plus side is the upper and the minus side is the lower, right? And so then things get mixed up. And so just remember that you have to always write them from smallest to largest. Okay. And so the lower is the p hat minus z star times the standard error of p hat, because I am getting sick of writing that square root, right? But it's the same. And the upper is going to be p hat plus z star times the standard error of p hat. Okay, good. So I had an example, but I actually like the example from the textbook. And where is it? I was obviously reading a little bit here. Now where is that darn example? It was an Ebola one, a quarantine one that I wanted. Oh yeah, here. Oh. So this is an example from the textbook that I want to go through start to finish. Okay, so in New York City on October 23rd, 2014, a doctor who had recently been treating Ebola patients in Guinea went to the hospital with a slight fever and was subsequently diagnosed with Ebola. Soon thereafter, an NBC4 New York / the Wall Street Journal / Marist poll, so they all got together, I guess, and did this poll, found that 82% of New Yorkers favored a mandatory 21-day quarantine. And it's only because we're talking a lot about quarantine and blah, blah, blah right now. So that's why I thought it was interesting. So a mandatory 21-day quarantine for anyone who's come in contact with an Ebola patient. This poll included responses of 1,042 New York adults between October 26th and 28th, 2014. Okay, so they only did the survey between October 26th and 28th, which restricts to the time frame that we could do inference for, right? And so let's just pick this thing apart, and then we're going to build a confidence interval for the proportion of people who support this mandatory 21-day quarantine. And maybe it's part of the here. Here's the follow-up question that I want to do. But let's do, instead of a 95% confidence interval, let's change it to a 90% confidence interval. And the 95% is in the textbook, so if you want to look at the 95, that's fine. But let's, just for practice, do a 90% confidence interval. Okay. And so, okay. In order to be able to build a confidence interval, we have to check the conditions first. Okay. We first check the conditions. So the first thing that we have to check is independence. The independence condition. Well, how do we check if the sample's independent, or if we can assume that it's independent? Well, we can make sure it's randomly selected. Now, let's see here. So this poll found that 82% of New Yorkers, and this poll included responses of 1,042 New York adults. And while we're here, I'm gonna just highlight that this is, oops, just our sample size. Yeah. And the poll found that 82%, so p hat is 0.82, because we're going to talk about the proportion that supported this mandatory quarantine, right? And so that's your p hat. Now, it doesn't actually say that the sample was randomly selected, but I think it's safe to say that if NBC4 New York and the Wall Street Journal and the Marist poll, if they all got together, it's safe to assume that it was randomly selected. Okay. So what we're going to say is we assume the sample was randomly selected. It doesn't say, but these are the assumptions that we're checking, right? And so we assume that it's reasonable to think that the sample is randomly selected. I am also going to include the optional 10% condition. Okay. The 10% condition says that my sample size has to be less than 10% or reasonably less than 10% of the population. Now, the population is the New York adults between October 26th and 28th. Okay, and so here, this is my population. I guess of 2014, but I'll leave that out. So is 1,042 less than 10% of the population of New York adults between October 26th and 28th of 2014? Yes, it's reasonable to assume. It is reasonable to assume n equal to 1,042 is less than 10% of New York adults. Yeah. Between October 26th and 28th, but I'm just going to leave it there. Okay. Because I'm also going to assume that that population, although it's constantly changing, but it's roughly the same and it'll always be less than 10%. Okay. So that's the independence condition. So then the normality condition is the success failure. So I don't have a population proportion because that's what I'm trying to find. Okay. But I do have p hat. So n times p hat, which is going to be 1,042 times 0.82, which I grab my calculator here. 1,042 times 0.82. And it's possible to have decimals here because usually we round the proportion and so it's not exact. So we have 854.44 successes. So 854.44 people out of 1,042 said that yes, they're in favor of this mandate, which is greater than or equal to 10. So I'm going to check that with the green check mark. And then NQ hat, there's a couple of ways that you could find it, right? You could take 1,042, subtract the successes, that leaves you with the failures, or let's do 1 minus 0.82 is 0.18. 1,042 times 0.18, 187.56, which is also greater than or equal to 10. So now that we've checked these conditions, so they're always going to check out, okay, but we do have to check them every time. So therefore, the conditions for constructing a confidence interval are satisfied. So we want to construct a 90% confidence interval for P, right? We're trying to capture that population proportion. And the P here is the proportion of New York adults who supported a quarantine for anyone who's come into contact with an Ebola patient. Okay, and so it gives us the proportion here, it gives us the parameter that we're interested in. Yeah, so we're going to save this, the proportion of New York adults who supported a quarantine for anyone who's come into contact with an Ebola patient, and then we're going to pull that out in our interpretation, right? But we don't need it for now. So our confidence interval is going to be P hat plus minus Z star times the standard error of P hat, which is square root of P hat Q hat over N. Now I have all these components, so it's just a matter of plug and chug here. And I do want to point out that you have this formula on that formula sheet I posted, but it's kind of out of order because it's in the old section of 6.1. Okay. And so here you have this confidence interval for P. I'll just bring it in so that you have it. Okay. So those are the areas that we're looking at right now. In fact, I'm going to bump this over so that I can have a little bit more room for it. There. Yeah. P hat, we know that's our best guess at the proportion of New York adults who favor this mandate. So 0.82 plus minus. Now, how do we find Z star? For a 90% confidence interval, right? I'm going to use this table that I created, copy. Put it down here. Yeah. And let's see here. So for a 90% confidence interval, Z star is going to be 1.645, right? So here I have 1.645. That's the only thing that dictates the width or the confidence level of my interval. Right? Times the square root of 0.82 times 0.18 divided by 1,042. So if I just plod through this here, I'm going to deal with, so I'm going to do the 0.82 times 0.18 first, then I'm going to divide by 1,042, and then I'm going to take the square root. Usually I take a pause there and I jot down what that number is, or if you prefer, you can just go straight through and find the value. But because we're just multiplying and dividing the order, well, as long as you do inside the square root first, it doesn't matter. So 0.82 times 0.18 divided by 1,042, and then I take the square root of that, 1.645 times 0.011901708878. Now, I'm going to keep all those decimal places because I always want to keep all my decimal places. Remember, proportions are always between 0 and 1. So you don't want to round too soon because then you're going to lose out on a lot of activity, right? And so here, so 0.82, and I guess copy. I'm going to put it here. So I have 0.82 plus minus, and then I'm going to multiply that by 0.1645, 0.01957831094. And then when I do this calculation, I'm going to subtract first. Now, most calculators have a store function, so you can figure out how to use your store function. So on this one, there's an STO button. So you can store this long value so you don't have to type it in every time. And I think the easiest way to figure it out is just to Google your calculator and just watch a YouTube video where they show you how to store stuff. But it's really handy. So I'm going to store it, and I'm going to store that in a value called A. Okay, so that's more for me, for you. So how I'm going to write this answer out is with these brackets, right? With the interval notation, I use round brackets and I separate the lower bound from the upper bound with a comma. Okay, so 0.82 minus that guy puts me at 0.80042168991 up to 0.82 plus recall A 0.83957831109. So notice how I'm keeping all my decimal places, and usually if I'm reporting a percentage, then I'll round to 1 decimal place for a percentage, or I'll keep 3 decimal places or 4 decimal places if I keep it as a proportion. Okay. So here, right, keep all your decimal places until the very end. Keep all decimal places until the end. Then round to 3 or 4 decimal places. Then round to 3 or 4 decimal places. The questions usually tell you how many decimal places to round to. And so that's why I'm kind of 3 or 4, use your judgment, right? For example, here, if I wanted to capture this 4, then I would round to 4 decimal places, but I should round to 4 decimal places in both cases, right? So, so here, I would write this out as 0.8004 up to 0.8396, rounding properly. So now, once we've built our interval, it's time to interpret this interval, right? Our job is not just to build the intervals, it's also to interpret these intervals, because building them is not the hard part. It's the interpretation that's the hard part. Okay, so we always need to interpret the interval. So we always need to interpret the interval. And in this case, we're going to say that now we can talk about the proportion, right? So this is if we have the proportion, or if we wanted to talk about versus 80.04% to 83.96%, the percentage. So it depends on what you want to talk about. Now, when I look at this question, right, it does ask me to construct a 90% confidence interval for P, which is the proportion, right? But they also reported a proportion as a percentage. So I think we can go either way, right? But let's do the proportion first. So we say we are And in this case, 90% confident. That the interval, from blank, which is the lower one, 0.8004, to blank, which is the upper, which is 0.8396, captures the population proportion of New York adults between October 26th and 28th of 2014 that support the mandatory quarantine. And so what I'm going to do, instead of having to memorize that, I'm just going to copy from here and clean this up here because we didn't, oh, actually we did change that. Okay. Captures the proportion of New York adults so here, the proportion of New York adults who supported a quarantine for anyone who has come in contact. So for this part, you really just reword the question as an answer. Who has come in contact with an Ebola patient. Nice. Okay, so we are going to build many confidence intervals, and I want you to always remember to interpret it, but also that you have the standard blurb that we're going to use for any confidence interval that we build. Okay, so that's where we'll end today, and that's the end of confidence intervals. I'll post a video for tomorrow starting on hypothesis testing, which is a big chunk of this course. And so we'll get you started there. And if you have any questions, let me know. Otherwise, I'll see you next week. Stop this recording here.